Hello dear student, myself Prof. K. Today we learn new topic electrical energy of 2-point charges and of an dipole in an electrostatics field. This is a next part in electrostatics chapter number 8. Electrical energy of an 2-point charges and of a dipole in an electrostatic field. In this chapter we basically discuss when two like charges lie infinite distance apart, their potential energy is zero because no work has to done is moving one charge at an infinity distance from the others. But when they are brought closer to one another, work has to be done against the force of the repulsion. As electrostatic force is conservative, this work gets stored as the potential energy of 2-point charges. Next, we can discuss another definition: electrostatic potential energy of a system of a point charges. What mean by electrostatic potential energy of a system of 2-point charges, or define electrostatic potential energy of a system of a point charges. Here we give one definition. Electrostatic potential energy of a system of a point charges is defined as the total amount of work done to be assembled to the system of charges by bringing them from infinity to their present location. What I mean by electrostatic potential energy of a system of 2-point charges? Electrostatic potential energy of a system of a point charges is defined as the total amount of work done to assemble the system of charges by bringing them from infinity for their presence location. This is the electrostatic potential energy of a system of a point charges. Then we discuss next point, an expression for potential energy of a system of 2-point charges. An expression for potential energy of a system of a 2-point charges. Consider 2-point charges. Consider 2-point charges Q1 and Q2. These 2-point charges Q1 and Q2 with position vector R1 and R2 relative to some origin. Suppose this origin is O here, as shown these figures. This is the system of 2-point charges. Figure shows that system of 2-point charges. Here no work is done while bringing first. Here no work done while bringing first charge Q1 to the position R1 due to absence of electrical field. Then no work is done while bringing first charge Q1 to the position A R1 due to the absence of electrical field. W1 is equal to 0. Now charge Q1 produces a potential in space given by V1 is equal to 1 upon 4 pi epsilon naught into Q upon R1. Consider equation first here. Here this R1 is the distance of point A from the origins, where R is a distance of point A from the origin. Work done to bring the charge Q2 from infinity to B of R2 is given by the verdants W2 is equal to potential at B due to charge Q1 into Q2. Then we know that the potential at B due to charge Q1, we can write here W2 is equal to Q1 upon 4 pi epsilon naught R1 R2 into Q2, where AB is a R1 R2. R1 R2. This is the work done. This is the work done. In bringing the two charges to their respective location is stored as the potential energy of the configuration of two charges. Then we can write here U is equal to 1 upon 4 pi epsilon naught Q1 upon Q2 upon R1 R2. Consider equation number third. This equation number third gives the required expression and can be generalized for a system of any number of a point charges. Some question asked on this topic: derive an expression for potential energy of a system of 2-point charges. Derive an expression for potential energy of a system of 2-point charges. Then consider next one, next point here. An expression for potential energy for a system of a n-point charges. An expression for potential energy for a system of n-point charges. We know that here U is equal to 1 upon 4 pi epsilon naught into Q1 into Q2 upon R1 R2. Consider equation 4. This equation first gives the expression for potential energy for a system of 2-point charges. In bringing a charge Q0 from infinity to C, R3, work done to be done against the electrostatic force of both Q1 and Q2. Then W3, another work done, W3, we can write this W3 potential at C due to Q1 into Q3, Q1 and Q2 into Q3. Here W3 is equal to potential at C due to Q1 and Q2 into Q3. Then we can write this 1 upon 4 pi epsilon naught Q1 upon R13 plus Q2 R1 R23 into Q3. Then we calculate here 1 upon 4 pi epsilon naught into Q1 Q3 upon R1, here R1 3 plus Q2 Q3 upon R23. Similarly, in a bringing charge Q4 and infinity to d of R bar 4, work has to be done against the electrostatic force of Q1, Q2 and Q3. Then W4 is equal to 1 upon 4 pi. W4 is equal to 1 upon 4 pi epsilon naught into Q1 Q4 upon R1 force plus Q2 Q4 here upon R24 plus Q3 Q4 here upon R34. The proceeding in the same way, we can write the electrostatic potential energy of a system of n point charges at R1 R2 R1 R2 up to Rn, as we can write this here. U is equal to 1 upon 4 pi epsilon naught summation of all points q suffix j into q suffix k upon r suffix j in r suffix j k. This is a equation and expression for potential energy of a system of a n point charges. Some question asked on this topic: derive an expression for potential energy for a system of n point charges. Derive an expression for potential energy for a system of n point charges. Then we can discuss another points. Potential energy of a single charge in a external fields. Potential energy of a single charge in an external fields. Here if Vr is the external potential at any point P having position vector r bar, then the definition work done in a bringing unit positive charge from infinity to the point P is equal to the V. As a result, work done in a bringing charge q to infinity to the given point in the external field is q into here q into Vr. This is work done is stored in the form of potential energy of a system of charge q. This is gives potential energy of a system of a single charge q at r bar in an external electrical field is given by this potential energy is equal to qv of r. This is a required equation. Some question asks here: discuss the potential energy of a single charge in an external field. Discuss potential energy of a single charge in an external fields. Then another term we can discuss here: an expression for potential energy and expression for potential energy of a system of 2 point charges in a external fields. Here 2 point charges external field. Let us system of 2 point charges q1 and q2 to be located at r1 and r2 respectively in an external field were done in bringing the charges q1 from the infinity to r1. Then p suffix e uh, potential energy suffix 1 is equal to w1 is equal to q1 into p r1. Consider equation first here. To bringing the charge q2 and r2, the work done not only against the external electric field. Suppose this external electric field is denoted by E, but also against the field due to q1 were done on q2 against the field. We can write this q2 into v r2 and were done on q2 against the field due to q1. We can write this q1 q2 upon 4 pi epsilon naught r12, where r12 distance between q1 and q2 by the principle of superposition for the field. These were done on q2 against the two field is work. Here two field is were done in bringing minus q2 here q2 upon r2. Therefore we can write this w2 is equal to q2 into v of r2 plus q1 upon q2 upon 4 pi epsilon naught r1 1 2. Using equation first and second, we get the total work done is assembling the configuration time. W is equal to q1 into v r1 plus q2 v r2 plus q1 q0 upon 4 pi epsilon naught 4 pi epsilon naught 1 r2. This equation number, consider equation number 3 here. This equation 3 gives an expression for potential energy of a system of 2 point charges in a external electric field. External electric field. This is equation number 3 gives an expression for potential energy of a system of 2 point charges in external field. We prepare some notes here. A spherical cell of a radius, suppose this radius we can consider small b, with charge capital Q, is expanded to a radius, suppose this radius we consider small a. Find the work done by the electrical force in the process. According to this, the electrical charges move radially as cell expands, as the electrical field in this case is here, as the electrical field in this case is conservative, here conservative, then total work done by the field force is given by W is equal to u suffix I minus u suffix f, then W is equal to 1 upon 2 q square upon 4 pi epsilon naught b minus q upon 4 q square upon 4 pi epsilon naught b, where W is equal to q square upon 4 pi epsilon naught, q square upon 4 pi epsilon naught into 1 upon b minus 1 upon a square, minus a square. Some question asked on this topic is spherical cell of radius capital B or small b with charge q is expanded in a radius e. Find the work done by the electrical forces in plane. Then most important point in the chapters, an expression for material or potential energy of an electrical dipole in an external electric field. An expression for potential energy of a system of electric dipole in a external fields. See this diagram. See this diagram. This figure shows that couple acting on a dipoles. Consider a dipole with charges minus q and plus q, minus q and plus q, separated by finite distance. Suppose this finite distance we consider toisiel, placed in uniform magnetic field. Suppose this uniform magnetic field is E bars. It experience torque T bars, experience torque toe bars, which tends to rotate as shown these figures. We can write toe bar is equal to P bar into E bar, then toe bar is equal to P sin theta. To neutralize this torque, let us assume external torque. Suppose this external torque we consider toe external be applied, which rotate in a plane of the papers from the angle theta 0 to the angle theta 0 to theta 0 to angle theta without angular acceleration, and were done by the external torque. Here were done by the external torque is given by W is equal to integration changes theta 0 to theta, then toe external into theta into d theta. W is equal to integration changes theta 0 to theta potential energy, here P into E into sin theta into d theta, sin theta into d theta. Applying integration rule, W is equal to PE into minus cos theta, integration changes or upper limit is theta and lower limit is theta 0. Here sin theta d theta is equal to minus cos theta, then W is equal to PE into minus cos theta into minus cos theta, then W is equal to P in bracket minus cos theta plus cos theta 0. Then rearranging this equation, we can write this W is equal to potential energy in bracket cos theta 0 minus cos theta if here if star gives the work done is stored as the potential energy of the system in the position when the dipole makes an angle theta with electrical field. Thus, the potential energy of a electrical dipole in external electrical field. Then theta minus here u of theta minus u of theta 0, then P into E into cos theta minus cos 0. uh, we can discuss here some special cases. First one, choosing uh, u of q0 is equal to 0. U of q0 is equal to 0. We gets the dipole is perpendicular to the field. The initial the dipole is independent to the field. E is equal E bars, that is theta is equal to pi by 2. Then u of r is equal to pe into cos, here cos pi by 2 is equal to 0. Then u suffix theta is equal to p into q into cos theta. Then v suffix theta is equal to p of u of q is equal to minus pe cos theta. Then u of q is equal to minus p cos theta. Therefore u of q is equal to minus p into e bar minus p e bar. Here and next case, if initially the dipole is parallel to the field, then e bar then q suffix 0 is equal to q. We can write this because here u theta is equal to 0. U suffix u of r is equal to pe in bracket 6. Here u of theta is equal to p of into cos theta minus cos theta. Here again u theta is equal to pe 1 minus cos theta. And the last point, if initial the dipole is parallel to the field e bar, then theta 0 is equal to this. U of theta is equal to pe cos 0 minus cos theta. Then u of theta is equal to p 1 minus cos theta. This is the 5 points we can discuss. Derive an expression for potential energy of an electrical dipole in external fields. Then we can discuss expression for potential energy for a system of n point charges. Then we can discuss an expression for potential energy of a system of 2-point charges. In this way we can complete this point in electrostatics. Electrical energy of 2-point charges and of an dipole is in electrostatics field. Today we stop here. Thank you.